So by now, I think you have a good idea of what cluster is, right? If somebody asks you, you can confidently tell, like describe what cluster is, correct? So I'll be talking about clusters only, but some aspects like, so you have studied that if you want to make clusters, you have to stabilize with them with some protecting ligands. So that's what you have heard from Professor Pradeep's talk. So normally we say that these ligands actually impart stability to the clusters, right? So what I will be showing is that that is true. It imparts stability, but it also can actually uh, make the clusters highly dynamic. And we can see this dynamics, the effects of this dynamics using chemical reactivity, chirality, etc. So that's what I will be going to talk about. And as Prakriti mentioned, I come from IISER Thiruvananthapuram. It's also a very beautiful campus, like this campus, not this large. It's about like 250 acres or something. So this is the overall view. But I have not seen any one like this, even though I put the picture. So I work on chiral inorganic and biological materials. So I'm sure that everybody here can identify who is this. Okay. So what did he do with the nanotechnology? I mean, he is the one who proposed the idea of nanotechnology, right? How, that also I'm sure that everybody will know. So that is by his one of the address at Caltech called "There is plenty of room at the bottom." So he basically, what he was proposing, that you can maneuver or you can handle atoms by atoms in a single atom manner. You can handle one atom by atom. So this is what he was proposing. So why should one do that? There should be something interesting, right? Otherwise, nobody will spend a lot of energy into that. So there are a lot of interesting things, as you have already heard a little bit. So if you have the ability to pick and arrange atoms, what you can make is that you can make groups of these atoms or molecules called clusters. So that is what. So clusters are nothing but the groups of atoms or molecules. So if that is what clusters are, uh, so clusters are as these are the small or divided forms of any materials you can think of, right? So you can have clusters of atoms like metal atoms or noble gas atoms, and you can have clusters of molecules like water clusters, for example, and you can also think of clusters of ionic compounds. So in principle, you can prepare this atomically precise forms of any material you want. So even nowadays, you can see the atomic precision people are trying to achieve in cadmium sulfide, cadmium selenide kind of quantum rods, very precise units like this. So if you want to know more about this world of clusters, I would say that you can read this book. It's a very nice introduction to the world of clusters. So why should we study clusters, for example, metal clusters? So one reason is that you can actually study the evolution of properties, right? You have actually studied different properties of metals, like what I have mentioned here, and chemical reactivity. There are many other properties. So one question is that, as Feynman proposed, can we make tiny forms of this matter by picking up single atoms by atom, putting and making this what we call as clusters, and then we will eventually reach the bulk material, right? So what happens to this, all of these properties in between? So that is one of the basic interest in doing nanotechnology. Like you can study the evolution of properties by creating such particles of different sizes and shape. And here is the crystal structure of your gold. This is a face-centered cubic, FCC cubic, right? FCC structure. Suppose you can ask this question, like if I have this many number of atoms as shown here, will they be arranged in this way, or the shape will be something different, or will it have chemical reactivity similar to bulk, or it will have something else? So this kind of fundamental questions we can ask regarding this clusters. So that is what makes it very interesting. Now, why this properties changes? One reason is that it has to do with the electronic energy levels, right? As you all know. So as you go from the bulk, which will not have any band gap like metals, the band gaps opens up, and in a size regime where below below 2 nanometer, what happens is that you will have discrete electronic energy levels like that you normally find in molecules, right? So that is the basis of the origin of the altered properties of these clusters. Now you can, as I told, you can make the clusters of different material, like this is the mass spectrum of water clusters, and similarly you can make the clusters of sodium chloride, or this you have already seen in Professor Pradeep's lecture. This is the mass spectrum of sodium clusters, right? So here we can clearly see that these represents clusters of different nuclearity. That means the different number of metal atoms. There are distinctly different intensities for 20 atom cluster, 40 atom, 58 or 8. So what does these numbers correspond to? This corresponds to the valence shell electronic configuration of noble metals, right? So one way to explain the stability of these clusters is that they have this noble gas-like electronic configuration, right? And how do we generally understand molecule? We have the basic properties of molecule. It has a precise molecular formula and it has a well-defined structure, then discrete electronic vibrational and rotational transition, then spectroscopic characterization, and it also has reactions, right? So this is how generally we understand how molecules behave. So what I will be showing is that we can do all these things which we normally do for the molecules in case of this ligand protected metal clusters. So this is one such cluster, one such molecule, as you will be now familiar with. This is gold 25. It consists of 25 gold atoms, and it is protected with 18 thiolate ligands, right? This is phenylethane thiolate. So this is its crystal structure, and so it has a precise molecular formula. Again, you have seen this, which corresponding to this molecular formula of gold 25 with 18 thiolate ligands. That is what you are seeing here. And I told about discrete electronic structure. You can see that it has multiple bands which can be described as due to the transition between different molecular MO energy levels, right? So this tells us that you can make this molecule and it satisfies the criteria that I told, that discrete molecular formula, electronic structure, and etc., and well-defined structure. So now the question is that next thing, what happens to its vibrational properties, right? So you can also study the vibrational spectra of these molecules. It should be possible in principle. So here is one cluster. This is gold 38, where you have two icosahedron are fused by sharing a phase. Okay, that is what you are seeing in the green color here. And there are the ligand units. I have not, the actual ligand is this one, and which is not shown in this picture, but it is in the form of this staples. You have listened before. And for this cluster, we can measure the Raman spectra of this cluster. What you are seeing is that, so in this region of the Raman spectra, you have the vibrations due to different the staple motifs, like which you call as radial breathing modes of the staple units. And if you go down this wave number, below 150 or 100 centimeter inverse, we can see that there are some interesting type of vibrations. That if you have a core like this, you can think of a breathing mode of vibration, right? So that you can detect at around very low wave number, like 90, 80, like this. So the core actually breathe in and breathe out. That's kind of vibration. And there are also some other vibration. You can see them, two central metal atoms here, gold atoms, and these can undergo some stretching kind of vibration. So different types of vibrational modes we can actually observe using Raman spectroscopy. And you can do this for many different types of clusters, and you can see here that these are different, distinctly different clusters, and they have unique Raman spectra. So you can have kind of vibrational fingerprinting using Raman spectroscopy for this kind of clusters. So what we have seen now is that it has almost all the properties of molecules that we have described, right? Now, what about their chemical reactivity? So it has passed all the other criteria. So will they react just like molecule? So that is what one of the things that we were interested in during PhD. So here we have two examples. This you have already seen, gold 25. This is another example of 44 atom containing silver cluster. So these are stable, highly stable according to various reasons, because they are all ligand protected heavily, and they have very compact geometric shells like icosahedron. Icosahedron is a very stable structure, right? And if you can also see that they all follow this noble gas-like electronic configuration. So we can say that they are stable because of the superatomic electron counting. Okay. So due to all these reasons, this is highly stable. So what we thought of, can we have reaction between them? So why we thought, I have to say why we got this idea. The idea is that here this is in this structure, the gold in this staple unit, these are in the gold +1 oxidation state. And suppose in this silver cluster, there are so many atoms in the 0 oxidation state, as silver 0. So as you know from the electrochemistry, when this gold 1 can be reduced to gold 0 by Ag0, right? This is known. So what we thought, if the two clusters meet, can such reduction occur? Can some reactivity like this occur between the two clusters? So that was a starting point of starting this intercluster reaction. Okay. So when we mix the solutions of these two clusters, something interesting happens, that they exchange metal atoms, ligands and metal ligand fragments between the two clusters. You have already seen this reaction before. And they can exchange between different sites. You have icosahedral site here, central atom, and here you have multiple shells. So you can ask a lot of questions like which one will go where and what is the associated thermodynamic preferences, etc. So how do we know that this is exchanging? Again, we have to go to mass spectrometry. So here we have seen that we can see that mass spectra of the two starting reactant molecules, let's say. So this is for gold 25 and this is for silver 44. So you can see only one feature here, which shows that they are pure. And the moment they mix, you can see that there are several peaks are emerging in the ESI mass spectra. If you analyze them carefully, you can see that this can be classified into different groups, like due to metal exchange alone, or ligand exchange alone, or metal ligand fragment exchange. So you can understand that this actually happens, and this happens in seconds or millisecond time scale in solution. It's very fast. Okay, and this is another example where you have two clusters which are structurally similar, but one is with silver and another is with gold, but they are having different ligands, but molecular weight is the same. So when you mix, the same metal exchange happens here as well. And what you can see is that this is the peak for only silver 25, this is only for gold 25. And if you zoom the region in between, you can see that there is an entire range of alloys are getting formed, but the total number of metal atoms is preserved in 25. So that doesn't change, but it can go from 23 or 24, 1 to 0, 24, like it goes in the entire range. And we could also detect the adduct, I mean, when the two clusters are reacting with each other, the one possibility is that you may be able to detect the adducts between the two molecules, right? So this is one we could detect. We could detect a dianionic adduct of silver 25 and gold 25. Okay, so this tells us that this could be one of the ways by which this metal exchange happens. So this does not rule out other possibilities. And so in that two examples, the metal was different, ligand was different, right? So you can ask this question: for this exchange to happen, should the metal be different or ligand should be different? That is a basic curiosity, right? So what Papri in Pradeep sir's lab, she has done is that she has synthesized silver 25 clusters in isotopically pure form. Again, you will remember from Professor Pradeep's lecture. And this will have the isotopically pure Ag25 will have this mass spectral features. The moment they mix, again we can see that they started exchanging the isotopes. Then you will get this kind of feature. And yeah.
How can we say that the like mixing these two compounds, that compound was how pure means?
Because we start with isotopic. We start with isotopically pure silver nitrate. We can buy the aluminum foil, silver foil in the isotopically pure form. Then you convert into silver nitrate. Then you can do the cluster synthesis with silver 107 and silver 109. So then you make the cluster and measure the mass spectra. They will look like this. When they mix, when you mix the solutions of the two pure isotopically pure clusters, they will immediately start scrambling, just like isotopic exchange that you see in water. Okay, so then you will end up with something like this, which you see normally. If you make do the synthesis with the normal silver nitrate and make the cluster, it will look like this. Okay, and what could be the driving force for this reaction? If you have carefully listened to Professor Pradeep's talk, you can answer. He had mentioned that entropy, right? Because there is no change in the bond, because we assume that there is no change in the enthalpy because of the isotope differences. So then the only contribution to the lowering of Gibbs energy is the entropy contribution. So this is something similar to this situation you have studied in thermodynamics, right? Have you studied this? The mixing of two different, let's say, noble gases, and what is the entropy change. So this is something similar to what you have studied in your BSc or BSc classes, right? So this is the driving force for this particular isotope exchange reaction. And this intercluster reaction has been taken forward by different groups, and different papers have come from different parts of the world, different labs. And so that was about dynamics that we could observe through chemical reactivity, exchange reactivity, right? So what about the dynamics of the ligands, right? So dynamics are, the ligand molecules are there with specific staple patterns, and how dynamic they are. And also, what is the dynamics of this metal core? How can we understand that, right? So you can do, for the ligand part, you can do proton NMR. And what we can see here is that there is, according to the crystal structure, there are some interaction between this hydrogen atom and the pi electron cloud of this ligands. So this you can observe by this proton feature. So if you increase the temperature, if you do the temperature dependent NMR, you can see that this is changing slowly. So that means that these interactions are actually going to vanish with different temperature. And more interestingly, in this picture, you can see, so there are three different types of metal atoms. One is in the staples, and another is in the 12 atom icosahedral surface, and one is in the center, right? So silver is one example where you can have isotope, right? Silver 109 can show NMR activity. So you can do silver 109 NMR to see if you really see three different silvers in this cluster, right? So what Giovanni has done is that you can do silver NMR, but he could see, it is very weak, but he could see only one feature here. So what does this indicate? Yeah, they are equivalent, or they will be rapidly changing their positions, right, within the time scale of NMR. So that kind of dynamics of metal atoms within the cluster, that also we can study using NMR spectroscopy. So the picture, according to the crystal structure, even though look like very static, they are highly dynamic. Okay. And another feature is that feature that molecules can have is chirality, right? So molecules can be chiral. And here is one example. This is a cluster containing 38 gold atoms with 24 thiolate ligands. And this cluster is chiral. So normally we have studied about chirality, like we should have chiral center, right? Different types of chirality you have studied, axial chirality, point chirality, etc. But here we don't have none of them. But this cluster is chiral, because the ligand that we use is an achiral one. This is phenylethane thiol. This is achiral. And gold, as you know, it assumes normally it assumes a face-centered cubic, so that we don't expect to be chiral. But this cluster as such is chiral. So why it is chiral? Because there is a some helical arrangement of this staples around this metal core. Okay. So then you can ask about, if it is chiral, then there should be possibility of enantiomers, right? So can we separate this enantiomers, and can we prove the existence of enantiomers? So then you will have to think about different techniques like circular dichroism, circularly polarized luminescence. You have heard about these terms, right? And for those things, you have to first know the polarization of light, correct? So it is by the interaction of molecules, chiral molecules with polarized light, we understand the differences between, or we differentiate between the enantiomers. So this is plain polarized light, wherein electromagnetic field is oscillating along only one direction. So that is what we understand as plain polarized light. And what is circularly polarized light here? So if the electric field vector traces a clockwise direction, then you can call it as a right circularly polarized light. And if it traces out a left hand in anti-clockwise way, you call it as a left circularly polarized light. And you know that chiral molecules will interfere differently with right and left circularly polarized. This was also taught by one of the lectures yesterday, right? So it is by the differential interaction of chiral molecules with left and right CP light, we are going to differentiate between them. But I wanted to ask one question here. So when we talk about polarization of light, why do we worry about only the electric field vector? Why not magnetic field vector? Is there any reason, or it is just a convention? Yeah, it is perpendicular, but can we also use the magnetic field vector to describe polarization? So I want you to think about and try to find answer. That is interesting. Okay. So now I told about different techniques that can discriminate or distinguish between enantiomers of a compound. One is called circular dichroism. You have all studied this, I think, right? So it is the differential absorption of left and right circularly polarized light by a chiral molecule or a medium. And similarly, if your chiral molecule is fluorescent, you can have a technique called circularly polarized luminescence, that if you look at the emitted light, you will have different intensities for left and right CP light. So that is called circularly polarized luminescence. And one, if you want to observe this CD feature, the one criteria is that your ground state geometry of the molecule should be chiral, right? And if you want to observe this circularly polarized luminescence, your excited state, especially the emissive excited state, should be chiral. So these are the two basic conditions for observing CD and CPL activity. So if you combine these two techniques, and that can actually give some insights into the nature of, or nature of the excited states, or origin of photoluminescence, origin of chirality, etc. in organic molecules. Commonly this is done in organic molecules. So before going to see the application of these techniques to cluster, so this is CD and CPL. What is the little primary effects that you observe in chirality before you study this CD and CPL? Optical rotation, right? So that is what you study as the optical activity, right? So here is a paper which says the optical rotatory power of water. So anyone is getting surprised by this title? It says that water can show optical rotation, which is not what we have, which is not according to what we have studied, right? So it is an chiral molecule. So it says that this molecular chirality is actually not required for one to observe optical rotation or chiroptical effects. So here it says that if you place water molecule in some particular orientation with respect to the polarization direction of light, it can actually show optical rotation. It has not been experimentally proven. So if you want to understand this more in detail, you have to actually learn a lot of physics. So this is that is why I wanted to put this here to tell that you have to read some more physics, then only you can understand some of the effects in greater detail. Okay, and so how do we apply this to the clusters? One work that we did is that we can do CD and CPL spectroscopy on clusters that can give an idea about the origin of chirality and photoluminescence in some cluster system. So we will not have time. This is done for a silver 24 gold 1 system. So we will not have time to describe this in complete. And some more application or some what different insights you can get from CD CPL experiments on clusters, that is also mentioned in this review article. And so I told that gold 38, we'll come back to this. Gold 38 example, it can be chiral because of the helical arrangement of staple units, and it will have enantiomers, right? So how can we separate them? You can separate them using chiral HPLC. You will have chiral, you have a HPLC column, you will coat with some chiral molecule, then you will be able to separate these enantiomers. As you can see, the enantiomers and the racemic mixture show the same UV features as expected. But if you measure the CD spectra of this, you can see clear mirror image relationship. So this is how you can prove that you can separate and you have got the enantiomers of this cluster. And now some other interesting thing. So this is again the same cluster, gold 38. You have a ligand here. This is the phenylethyl thiol, which is achiral. So it is, if you look at this particular conformation, this is having a chiral geometry. Even though molecule in the normal state it is achiral, but on the cluster surface this has a chiral configuration. So how do we detect this? So one way to do that, what is called vibrational circular dichroism. In the previous example, it was electronic circular dichroism, where we probe the chirality in the electronic transition. Here we can probe the same thing, circular dichroism we can use using the infrared radiation. So that can probe the chiral conformation of molecules and in conditions like this. So what we can see is that this is the IR spectrum of the cluster, which will be the same for both the enantiomers. But if you look at the VCD spectrum, again we can see clearly there is a mirror image relationship. So this tells us that this achiral molecule can adopt some chiral conformation on the cluster surface. So we can understand chirality of these clusters using these different tools. And what would be the most symmetric or beautiful molecule that you have studied or come across? CH4. Yeah, beauty. Forget about beauty. I mean, beauty and symmetry is not very much related, but most symmetric molecule. C60, right? So C60 is most symmetrical. So is it possible to induce chirality in that? So that's an interesting question, right? So what people have done is they could induce chirality in C60 by putting them in some chiral environment. Like they have put C60 fullerene in some chiral metal organic framework, and they could observe circular dichroism features corresponding to the C60 spectra. So here what we can see is that this is the picture. This is C60 and putting in chiral metal organic framework unit, where you have a lot of pi-rich ligands here, which can interfere with the pi electron cloud of C60, right? And if you look at the MO picture of C60 alone, it is symmetric as we expect, but this is perturbed by the interaction between the pi electron cloud of the MOF, chiral MOF. So that is what you see. And here is a proof that corresponding to the UV bands of C60, you can see the clear mirror image of mirror image CD bands for depending on the enantiomers, which enantiomer of the MOF is there. Okay, so this tells us that chirality is a geometrical property, which is true. But basically, what happens? Why all these things happens? Because of the interaction with the electronic charge cloud of the molecule. Okay, so and now we come to some other type of material where you can make clusters. So far we have seen that you can make clusters using organic ligands, right? Phenylethyl, thiol, etc. Can we make using some other ligands like DNA? Because DNA has several nucleobases like ATGC, and this G and C has high affinity to metals like gold and silver. So can we make clusters with that kind of ligands, let us say? So we can make, you can make them using simple wet chemical reduction like what you do normally for the other cluster synthesis. And so this is one example where people have solved the crystal structure of one of the clusters, DNA templated clusters. Here we can see that, so this is a 16 atom cluster with 2 chloride ion, and which is wrapped by 2 DNA ligands, DNA strands, single stranded DNA. So the DNA that is, I have not shown here. So 2 DNA are wrapping around this silver 16 2 chlorine core. And it also has very well defined UV features, just like U25 or AG44 that we have seen. Now, you can ask this similar question. So this is an emerging field, like people have made DNA templated clusters, but mostly they were focusing on their photoluminescence. So they were not much worried about the structure, their chemical reactivity, etc. So if you have such a atomically precise cluster, you can ask the similar type of question that we asked in the case of other clusters. Can they exchange can they do this intercluster reactivity, just like what we have seen? So it is again demonstrated that people could make isotopically pure clusters of this kind, and they indeed show this exchange reactivity. Okay, but in this case, as you can expect, this will be much slower because this ligand acts as a bidentate, right? It is completely wrapping. It's not a single point contact. So in this case, this exchange happens in minutes, unlike the other case of isotope exchange, which happens in milliseconds or seconds. Okay, and now again, DNA is inherently chiral, right? DNA is inherently chiral molecule. So one can ask, can these clusters show some interesting chirality, chiroptical properties? So if you have such a cluster, we can ask a number of questions. Will the metal atom arrangement be chiral? Inside the chiral template, will the Ag16 core will be chiral or not? And if it is chiral, why it is chiral? Like, is it because of the templating effect or something else, right? So that is what we call as mechanism of chirality induction. And if can these clusters exhibit some dynamical chiral response? That is, you know that DNA is a dynamic molecule, right? So you can, it has a different, it has a large conformational landscape, which you can tune by adjusting the pH or by adding metal ion or temperature. You can change the conformation. So if you do that, can we observe some interesting dynamic chiroptical activity for these clusters? And can these be used for chirality related applications? So that is the another question, right? So you can ask this kind of fundamental question if you have such a chiral cluster. So how do we know if the core has a chiral structure? One is that, for example, this is the UV spectra of a 10 atom cluster which we have synthesized. It has a band at around like 490 nanometer, and it is known that this band is due to the transition involving the metal core. Okay, and if you measure the CD spectra of this cluster, what you can see is that corresponding to this band, there is a weak CD band over here. So this tells this is an indication that this silver 10 core can be in a chiral geometry. So it has not been proved, the crystal structure is not known yet, but this coinciding UV and CD feature tells that actually the cluster core can be in a chiral geometry. And again, as I told, can we tune the chiroptical properties using different stimuli? So one is that you can do temperature dependent CD spectra. So what you see here is this the same 490 nanometer band that that you have seen before here. So you have this band here, and if you increase the temperature, we will see some interesting changes here. So initially we start from 5 degrees centigrade, you have a small band here with a positive cotton effect. And if you increase the temperature slowly, this comes down and then CD intensity slowly goes on, right? And if you reduce the temperature from 80 and back to 5 degree, what we can see is that these changes slowly, this slowly go back to almost its original condition. That means this chiroptical properties can be, or CD spectral feature can be changed by applying temperature. So this could be due to that the metal geometry is undergoing maybe from one chiral geometry to another. Again, we don't have more evidence, structural evidence for that right now, but this could be what is happening in this case. And this cluster is luminescent. So I told that, so this is two silver-10 clusters synthesized with two different DNA ligands. And what we can see is that in UV they look very same, but in CD you can see that they appear as a mirror image with some slight shift is there. But otherwise they look like a mirror image. So we can see that if you use different DNA sequences, we can actually change the chiroptical properties of these clusters. And more interestingly, like I told that they show the photoluminescence, which has a peak around 550 nanometer. And you can see again, I told about CPL, right? Differential emission of left and right CP light. So it shows, this also shows some mirror image relationship for these two clusters. So this is the first time we could observe this distinct CD and CPL features for this type of clusters. So this also shows that this dynamics or the chiroptical properties of these clusters can be tuned by using different DNA sequences. And there are some other clusters with at least the composition is known. For example, here is the case of silver 17 cluster, again stabilized by two single-stranded DNA. Its structure is known, but it can be isolated through HPLC and you can get in a highly pure form, and you can measure the mass spectra, everything. And what about its chiroptical properties? Like here is a CD spectra that we measured at different temperatures for this cluster. But we can see that it is very stable even up to like 80 degree. There are small changes that is happening at around 70 80 degree for the features, but overall this is going to be highly stable. So when we normally think of DNA, this is highly dynamic entity. So one question is that, are these clusters also highly dynamic, structurally dynamic? So one way to study that aspect is to do temperature dependent CD. So here we see that this is highly robust, structurally highly robust, and you can, even whatever small changes is observed, it is almost reversible when we go back in temperature. And similarly, the other cluster we have studied is silver 16 cluster. We can see that this is also highly stable, and even at this large temperature range, nothing much happens to the CD features. So despite the dynamics of the DNA ligand, actually this cluster is highly structurally robust. That is what we can prove from this temperature dependent CD. And we can also use this for conformational changes, to probe the conformational changes of the DNA. So one is that this is for, again, silver 16 chloride system, where you have, this is the DNA that is used for the synthesis of that cluster, and in the unbound form or pure form, it will exhibit a CD feature like this. And it is known that if you add metal ions like silver, it can actually form DNA mediated base pairs. So that means if you have a DNA like this, in order to incorporate silver atoms, it can actually bend, and silver will be incorporate complex between the different bases of the same strand. And in that case, the DNA, the single-stranded DNA will be in a bend form. So in the unbound form, it will be in a linear fashion, but when you incorporate Ag plus ion, this will be in this bend conformation. And for this cluster, if we measure the CD spectra in the same region, we see that this the spectral patterns are same for the DNA complex and for the cluster form. So what we can understand from this is that the DNA in this cluster may be adopting the similar conformation in the cluster form. So this is what already reported from the crystal structure, where we can see that the cluster, in the cluster, this DNA strand is actually bent. So which we can also observe using CD spectroscopy. So the conformational dynamics of the DNA can also be probed using CD spectroscopy. And so this is silver 16 but templated within DNA. So can this be chiral? Can there be a chiral geometry for this silver 16 Cl2 core, right? So that will be interesting to find. And we know that by changing the temperature or by changing the other factors, you can tune the conformations of the DNA. So we may, at some point, we may be able to induce some chirality in the geometry of the metal core. So we wanted to see whether that is happening or not. So what we did is, again, temperature dependent CD we did. What we can see is at across this large temperature range, we don't see the emergence of any bands corresponding to this. So if you remember, there was in the UV spectra of this cluster, there was a clear band at around 520, which is the signature of the metal core. But we do not see any emergence of that feature in this temperature dependent CD. So which tells us that it's in a completely it's in a chiral form, and that it's also structurally robust. So it is not that since you have a chiral template, it may not show the chirality in all levels. Okay, so that is one thing that we can understand from this CD studies. So what we have seen, what we have learned from this is that you have ligand stabilized clusters of different forms. It can be small organic molecule protected or DNA protected or protein templated. So it imparts stability, but at the same time, it can be highly dynamic. And this dynamics can be observed using a number of tools like vibrational spectroscopy, Raman spectroscopy, that's what I have shown, NMR spectroscopy, or it is also evident in chemical reactivity. And you can also study the dynamics of these clusters using different tools like CD, CPL, or etc. So that is what I would like to show you today. And I would like to thank Professor Pradeep. And these are Professor Thomas Burgi at University of Geneva, Professor Luis Lismarzan in Spain, and Professor IISER Cortajarena. They were the postdoctoral advisors. And these are the current group members. And I also would like to thank Professor Jain Murthy and the other faculties there, Professor Rajiv Varghese and Professor George Thomas, and also the funding agencies for money, right? So I finished so early, I think. So you can have any questions.
We have time, we can go for many questions.
Sir, I have a question. Like in one of the slides, you have shown that the temperature change, there is a change in the chirality. Like
yes.
Slide number 40 or something.
Yes.
No.
Yeah.
Yes, sir. This one, like from 5 degree to 80 degree, and from 80 degree to 5 degree, there is a change in chirality.
Yes.
So does that change in chirality means the D form, like we will have the D form or the L form, like levorotatory or means right hand circularly polarized. I mean levorotatory or dextrorotatory, like that.
Yes.
So will that get changed, or like if the molecule which is having levorotatory will change into a dextrorotatory like that, because the cotton effect is getting changed, like the negative is changing to the positive cotton effect.
Yeah.
So will that get changed with the change in temperature?
So here the chirality exists in different levels. One is the chirality of the DNA. So DNA will have some chiral arrangement of its nucleobases. So that seemingly is not changing. So I have not shown the region where the DNA absorb. DNA absorb normally below 300 nanometer. Above, there is no features for that. And if you observe the CD features below 300 nanometer, that doesn't change the sign with temperature. So that means the conformation of the DNA change, the chirality of the DNA does not change. So DNA exists in some particular chiral geometry. For example, if the nucleobases are arranged in a clockwise fashion, that remains as such. But there can be small changes. You can see small difference in CD intensity. But no, overall, that does not change the state of chirality. But here, this may be due to the change in chirality of the core. Okay, this may be due to a local change where the conformation of the silver core will be changing from one chiral geometry to another. Whether they are completely truly enantiomeric or not, that we don't know really. So it is not very simple to, the chirality actually is a complex thing, and it is even more so in this kind of system. So we cannot clearly say whether it is simply changing from one dextrorotatory form to levorotatory. So that is difficult to say. But we think that this could be due to the change in chirality of the metal core.
But so you are inducing chirality in the metal core by using DNA.
Yes.
DNA is not changing, like the chirality is inducing because of the DNA itself.
Yes.
And you're saying that the DNA does not change.
Yeah. So she's asking, I told that DNA does not change its chiral form, right? That's what I told. Why the chiral geometry of the metal core is changing? It could be because of some local effects, like because compared to the whole DNA ligands, this silver 10 is a small part. So even if the nucleobases are attached to the silver 10 core, which is very small, so even some small change in the nucleobase orientation can actually alter the little geometry of the silver 10, right? So that will be reflected in its associated electronic bands. So that could be the reason. So as of now, it's not completely proven because first of all, its structure is not known. So what we could infer from this CD spectra is like this. Yeah.
So, we're talking about how to prove the conformations using this video.
Yes.
Can you once again talk about it?
Here, right? Yeah. So here, what I wanted to know is that this is the DNA ligand that is used for making the cluster. So in the pure form, it will have a linear form, and DNA can actually form some secondary structure like hairpin, etc. But in this case, it is known that it does not form any hairpin or any other secondary structures. It exists in a linear form. And I wanted to know what is the change with respect to this one. What is the change of conformation of DNA when it is bound to a cluster? And when you make the cluster, you mix the DNA solution with your metal salt, silver nitrate. So when you do that in the beginning, before you add the reducing agent, it can form DNA metal complexes. So in that case, it is known that it can form silver mediated base pairs, in which case the DNA will adopt a bend geometry. So I wanted to know at what stage it is in the cluster form. So that is why I compared the CD spectra in the same region for all these three cases.
As it's bending, the CD is changing.
Yeah, that will change. Yes, yes. So that is why, like in this way, it has a particular shape here, which is different from the other two cases. So the CD spectra is similar for this complex case as well as the cluster case. So which is an indication that the conformation could be similar. So, and actually this is much more complex. The thing is that I don't know, maybe you have studied the conformation of DNA like different forms, A form, B form and Z form. You have studied, right? So this conformation actually refers to the packing of the nucleobases, not really this overall geometry. So that is a bit complicated, but you can get an overall picture of the changes by comparing the CD bands.
Now, if we take the middle one,
Yeah.
Can we exactly say, looking at the CD, that this will be the bent one and not the something else? It could be like
because if you see like this, most likely it will be in the bend form. But in this particular case, it is also true because in the crystal structure we can see that this exists in a bend form.
Like, is it a signature for that?
Yes.
Specific for that?
Yes. Yeah. I mean, it is not just it can be a range of geometries, but the CD will reflect only an overall feature. Okay.
One more question.
Yeah.
In the water example that we talked about, water though is not chiral,
yes,
but it was showing CD.
Yes, it will show optical rotation. Yes.
Because of optical.
Yeah.
So in that way, can we also think like molecules, if it could rotate, could also show the CD, but it might not be chiral?
Yeah, that is what this paper says. This paper says that molecule need not be chiral in order to see whatever chirality effects that we have studied, like optical rotation, CD, etc. So that is the basic message from that.
So when we are referring to a CD and saying, so yeah, this is the chirality of the molecule looking at CD.
Yeah, most probably it will be true because
yeah,
it is.
That's most probably, but it
Yeah,
could also be.
Yes,
Rotation,
yes, yes.
We are not taking that.
No. That is because we have studied in this way. I mean, textbook were mentioning in this way. But actually, if you look at the actual reason for optical rotation and CD, if you look at the physics of that, that paper describes that at some particular condition, it can actually do optical rotation. So that is what, and people, they were also suggesting that, I told that at some particular orientation of water molecules, right? So they suggested, as you know, ice will have different phases. So at some phase, they will have this expected some particular orientation of water molecules, which they propose will be ideal for testing out this optical rotation experimentally. But that has not been reported, I think.
That would be too ideal to be happen experimentally because that attaining that was that kind of orientation for the water molecule.
Yeah, that
they are doing it computationally.
Yeah, this is only computation.
So experimentally, it would be too ideal to attain such kind of orientation.
Yeah, that is why, like, ice has different forms, right? Different phases. So at some phase of ice, it has this particular orientation, and they expect that in that orientation you can actually observe. If you take such a crystal of ice and if you do the if you measure it in a polarimeter, you may observe the optical rotation, but it has not been proven yet.
Sir,
Yeah.
just by using the CD, then we can say that this one is R configuration, this wavelength is S configurations.
No, we cannot say. No.
And what was the optimum goal binding us AG with the DNA?
In this case, silver 10.
Okay.
So this will change, like as Professor Pradeep mentioned, here also people make this in a trial and error way. There is no guidelines to make, if I want to make silver 25 with DNA, we don't have that kind of ability yet. So people try different procedures and then optimize something, and then they can purify. Nowadays you can do HPLC and things like that to purify and crystallize.
Also, I have my background is a pharmaceutical
Okay.
background.
Mm-hmm.
So there is one drug came in 1960 in market. It's called thalidomide.
Yes.
It is a chiral molecule actually.
Mm-hmm.
It have R and S configuration.
Yes.
So
Thalidomide tragedy, right?
Yeah, thalidomide.
Mm-hmm.
So it given to the pregnant woman for motion sickness actually.
Yes.
So the R configuration for the motion sickness and S configuration for the teratogenic effect on the child.
Yes.
So when it given to the pregnant woman, it bind to the S configurations. That was the tragedy was happening. So what I wanted to know that the silver was bind to the DNA.
Yes.
Whether it bind to the R configuration or S configuration, what was this optimum goal to doing this?
Here there is no R and S here. So we cannot simply give an R and S notation for this kind of system. That is for your normal small molecular system. You can have this notation. But here it is not possible. And just to answer your question, like there are so many efforts going on, like because biology is chiral, right? Biology functions because of chirality, right? Chiral effects. So there is a lot of effects going on. What is the interaction of materials or materials with different chirality in the biological cells, etc. Lot of studies are going on. And as you are from pharma background, you should learn more about chirality. Okay, that will be very interesting.